even after the due date. That is, I mean, it will be accepted. Okay. Okay. So let me share the presentation for today. Let me just go through. Is this visible?
Yes, sir. Yes, sir, it is visible.
Yeah, thank you. So yesterday we discussed the special case of radioactivity, charging, discharging capacitor, and growth decay current are not, I mean, demonstrated here, but of course those can be discussed as assignment and can be discussed also over tutorial in case there are some people have problems with simulating that. Okay, today we shall go. Okay, what we can do is we can take one of the case here and we can discuss that, but that also can be done with the second order. So when you have, for example, LCR circuit, it becomes a second order differential equation, and we can discuss that. So let me go to the next slide, and we had discussed this yesterday. Just a minute, let me admit. So we had discussed this, and we said this is what we are going to iterate. Okay, and here we are not actually doing integration in a sense of using Simpson's rule, complete the integration and get the solution. We do the addition on the go as time progresses. Okay, and we look at the solution as a function of time. Okay, so that comes under the Euler's method of solving differential equation. Now, using numerical techniques, of course. Now, what we shall do further is, I mean, this we had considered. This will be given as one of the assignment, that if you have more, I mean, A disintegrating into B, B disintegrating into C, and even you can have larger series. Okay, we saw some of the features here. For example, the A start disintegrating, the B is, as A disintegrates, the B is getting created, and B is also getting disintegrated at its own rate, and the C gets created. So ultimately what happens is, the over a long time, you observe that the B starts from, say, 0, and then it reaches a peak, and then again it starts disintegrating. And how much peak it will reach, that depends on the half-life of A and as well as B. So if B has greater half-life, then of course it will reach higher peak. But if B has very small half-life as compared to half-life of A, then what will happen is B will get created and it will immediately get disintegrated. So it will never reach a very high value. Also, we observed one interesting thing, that see, what is the observable? Observable in any experiment is not the number of atoms directly, but it is the activity in this case. Okay, so how many atoms are disintegrating? And typically every, if you consider the natural radioactive series, okay, every atom is going to get disintegrated typically with alpha decay, and every particular element has a particular signature energy for that particular alpha emission, which means alpha emissions are generally monochromatic, mono energetic. Okay, and a particular source will generally give out alpha particle of that energy. And knowing the energy of alpha particle, one can find out that whether alpha particle has come from this particular disintegration or another disintegration. And then what one observes is, when after a sufficiently long time, the activity of each of the element in the series remains the same. So whether the amount of A and amount of B, they could be different, okay, but the activity remains the same. Activity becomes equal. What does that mean? It means that if B has higher activity, smaller half-life, okay, the amount of B is going to be less, but it is going to disintegrate more, and ultimately the product becomes equal to disintegration of A, and that is what we observed in one of the graphs, that A and B were almost becoming equal. Okay, now these kind of things graphically one can quickly calculate using Excel, and graphically one can see and understand some of these features. Of course, these features can obviously be understood using the analytical expressions, but for some people, graphical expressions are easy to understand. Let's go for, I was just waiting, people are coming. Let's go for a case of, say, simple harmonic oscillator where second order differential equation comes into picture. Okay, so let us take a case where force is minus kx1, and there could be a damping term that the force, the restoring force, is also going to be dependent on the velocity of the particle, and then this is going to be, B is going to be the damping constant. Now, numerically, when you want to solve this, what you can do is you can calculate the acceleration as force upon mass, and in most of the cases, we will consider say mass as a unity here, and we can see how the nature looks like. Okay, and one may then take k also as unity, and then omega becomes root of k by m from analytical solution, and that effectively becomes 1. How do we iterate these things? So first, knowing in acceleration, we can calculate the velocity. And what is the relation between velocity and acceleration? So we know acceleration is dv by dt. So we can write it as delta v upon delta t, or velocity can be written as delta v multiplied delta v equal to acceleration into time. What is delta v? It is v2 minus v1. So you may write the new value of v2, or the final velocity, is going to be the initial velocity plus a into delta t. Now, when we say final and initial, it is around this delta t. So you have taken one particular time interval. At the beginning of the interval, the velocity is v1. At the end of the interval, velocity is v2. Okay, and we are taking such small intervals, and we are calculating the velocities at the end of the interval based on what is the velocity at the beginning of the interval. So we are going to write this. Similarly, the displacement is going to be a function of velocity. So you will say the new displacement is going to be the earlier displacement plus v into delta t. Now here we can realize that though the expression says that this will go on increasing, it is not necessary, because value of a can be positive or negative. Okay, so depending on that, the velocity value or v2 value can increase or decrease, and based on values of v2 and x2, you will determine the force for the next iteration. So you will determine the force. Based on that, you will calculate what is going to be the acceleration. Based on acceleration, you will calculate the v3 value. So v3 will be v2 plus a into delta t, and x3 will be x2 plus v into delta t, and so on. And again, based on this v3 and x3, you can calculate for the next iteration what will be acceleration. So acceleration is going to be dependent on position as well as velocity. If there is a damping force, also velocity. Okay, so we need to see, we can see that how this can be simulated. Okay, and then of course you are going to repeat this cycle, and you will do whatever number of iterations you want to do. Okay, now yeah, two-dimensional problem will come a bit later. So let me come to the Excel. So I'll stop this presentation and start an Excel sheet. So we share Excel sheet. Okay, is this sheet visible?
Yes, sir.
Yeah. Okay, so we are solving this particular problem. Let me just write that problem for reference here. That f is equal to minus kx minus bv. Okay, this is the equation that we want to. This is the restoring force, and we are going to take mass as 1. So let me write the value of dt and t. So t minimum value and t maximum value I can decide, and I can find out what is the increment in time. And remember, we know that I mean, this is the kind of template first we are making. And suppose I want to iterate for say 1000 points. Okay, so I may determine T max say 10 and T minimum is 0. Okay, and I'm going to write T here, and I want to calculate the acceleration, velocity, and displacement. V, A, V, and X. Okay. Now, what are the constants of the problem? So, constant of the problem, K is one of the constant and B is another constant. Okay. So, first what we shall do is, we shall keep the damping constant say 0 initially, and K I'm going to keep 1. Okay. Now, just a minute. Just a minute. Yeah. So, this T, I'm going to keep T minimum. I mean, this, and the first part of the template, I'm just writing every time what we do. So it is A5 plus, I'm going to log this $A, $2, and copy and paste it in all 1000 cells. Okay, so the last value is 10. That's correctly observed. Okay, now starts, we have to write at t equal to 0. What will be the acceleration, what will be the velocity in displacement. So we are not the initial value of velocity and displacement we are giving. So initially, let us suppose there is some displacement I have to give, and velocity is 0. What does that mean? This is simple harmonic oscillator problem, we know. So you are going to start the oscillator from some particular extreme position. Okay, and you are not giving any velocity, that which means you are just stretching that oscillator and you are going to release it. Okay, if you give velocity and if you don't give displacement, then the system is at center and you are hammering it. Okay, so the initial condition will depend on whether you are stretching the system, whether you are stretching and hammering, whether you are only hammering it at the equilibrium position. All these things will happen. Now what we are going to do is, see, we have to calculate velocity based on the acceleration. So now acceleration here, I'm going to say acceleration I'm going to calculate later. So acceleration becomes minus kx minus bv. Okay, so it is minus k is written in E2 multiplied by value of x. Okay, minus p is $2 into velocity. Velocity is in C5. Okay, so I have written this. Now what I'm going to do is I will calculate velocity based on the earlier acceleration. So the new velocity is going to be the old velocity value plus this acceleration. Okay, the acceleration in the earlier step that we have calculated. Okay, multiplied by delta t, which I am writing as $A, $2. Okay, so this is the velocity calculated at first t. Now, so I can copy the same formula because all relations are same here. But see what is happening in this formula. In this formula, I am saying d6 is equal to d5, that is the earlier displacement, plus earlier velocity, the velocity in the earlier term, okay, multiplied by delta t. So this is the new displacement. And based on this displacement and this velocity, we'll calculate what will be the acceleration term. And I can copy that from this formula. So here, see again what is happening. It is minus $E, $2, which is minus k. And now I'm talking about D6 and C6, which is the present value of x and present value of y. So see what I'm doing is velocity, when I'm calculating new, I'm taking the old value of acceleration, I mean old value of acceleration means at the beginning of the time interval. Okay, and when I'm calculating the new position, I'm taking the velocity at the beginning of the interval. And now what I will do is, based on that, I'm going to calculate the acceleration. So now what I can do is I can copy this formula till end of the cells. Okay, so I've done that, and I will now.
Sir, can you please repeat again for B6, the formula and all B6?
Yes, I will do that. Okay, see what I've done. I have D6 you are saying, or B6 you are saying, E or D?
B, sir, B
Okay,
for
so
ball.
yeah, so B, what I'm doing is I'm calculating acceleration based on the velocity and displacement at that particular time interval. Okay, so I'm writing here minus E dollar E dollar 2, which is nothing but K value, multiplied by D6, which is X value, so minus KX. And second term is minus dollar F dollar 2, which is B value, right now it is 0. Okay, multiplied by C6, which is the velocity. Is it fine? So acceleration I'm calculating as minus Kx minus BV. Actually, it should be minus K by M X minus B by
Yes, sir.
M. I'm going to take M as 1. Okay, so if you
Okay.
want, I can write that specifically M equal to 1, and I can put that in the formula itself. Okay, so I may say divided by dollar G dollar 2 and divided by dollar G dollar 2. Okay, and then I can copy the same formula everywhere. The things are not going to change, but fine. I mean, at this moment, let us write that way. Okay, let me admit people. Yeah.
Thank you, sir.
Now, what we need to do is we need to plot all these things. So let us plot all this and see what is the plot that we get. We will get 3 series basically. Okay. Now here there is one thing, one procedural change I'm going to make. You are getting this. I mean, you are getting sinusoidal motion. So the first series is acceleration. The second series red is in velocity, and the third series is in displacement. Okay, in the green. Fine. The procedural change that I'm going to make here is this. I will not calculate acceleration at this point. And this acceleration I'll calculate based on the earlier value of velocity and displacement. Okay, so I'm going to make that change. I'll tell you why I'm going to make that change. Okay, it is a small trick, but I realized that I had made a mistake. But I will explain why it is happening. Fine. So what I've done is I'm calculating the fresh acceleration based on the earlier positions. I think probably I had written the same thing in the PowerPoint, but I use the other logic here. So I'm calculating new acceleration, and the velocity I will calculate based on the same acceleration. So now let me change this old velocity plus instead of B5, I will write B6. Okay, and I'm going to write C6 here. Okay, I will explain what I have done, and I'll also explain why I have done. So what at t equal to 0, velocity and displacement, 2 initial conditions are given. Why 2 initial conditions? It is second order differential equation. You will need 2 constants of integration if you want to get a solution. Okay, and those 2 constants of integration are the initial conditions here. What is the value of x at t equal to 0? What is the value of x dot, which is velocity at t equal to 0? Okay. Now our iteration steps are, let me just go back to the presentation, and I will show you what was done there. So yes, what is written here is V2 is V1 plus acceleration into delta t, and x2 is x1 plus velocity into delta t, and based on this velocity and acceleration determine the force for the next iteration. So actually we'll calculate the force okay, for the same iteration. Okay, I mean, sorry, the force for the next iteration you will calculate based on the earlier values of velocity and displacement. Okay, so keeping this in mind, let us see what we are doing in our Excel sheet. So use values of velocity and displacement in the next iteration for acceleration calculation.
Excuse me, sir.
Yes.
Sir, in the Excel, can you rub it all and do it once again? That from X, V, and A, so that it will be clear.
Okay, fine. Let's do that. Okay, and let's avoid the confusion. So at t equal to 0, velocity is 0, displacement is, I have given some 1 displacement. Fine. Now using this value of velocity and displacement, I'm going to calculate what is the new acceleration. So equal to minus k, k is in $E$2, into x, which is going to be in d phi, divided by m, so $G$2 minus bv upon m. So b is written in f2, so $F$2 multiplied by v is in c5, and divided by m, $G$2. Okay, so this is the acceleration we have calculated based on the earlier velocity. Now based on this acceleration I'll calculate the velocity. So velocity is equal to the old value of velocity, on top of that this acceleration multiplied by delta t, which is $A$2. And the same formula I can copy here, because the relational the relations are, positional relations are same. So d phi is the earlier displacement plus c6, which is the velocity multiplied by delta t, $A$2. Okay, I'm going to copy this up to the last cell. So last cell here is D1005. I copied this. Now what I'm doing is I'm going to plot the graph. So let me select all this and let me plot the graph. So I will insert scatter plot, and you have seen that even in Python you can use that scatter plot and you get this. Okay, now it is giving me certain amount of oscillations, because omega remember was root of k by m. K is 1, m is 1, and therefore omega turns out to be 1. Okay, and then within time 10 you can see how many oscillations are completed. It is slightly 1.5. So so approximately at 2 pi time, okay, you are completing one oscillation. Fine. Now let me make maximum time not as 10. I want to take more oscillations, so let me take it something like 50. And you see that large number of oscillations are there. I make it 30. And here what you have to observe is some specific things. First, some learning exercise. What is it? The blue curve is acceleration. Let me increase this font. Okay, blue curve is acceleration. The displacement started from 1, and velocity is going to be negative because you have stretched the object. So first it is going to come back. The acceleration is going to be in the negative direction. Okay, and it will come back. Now you can change the initial positions, initial conditions. Suppose instead of I have stretched the spring in this direction, if I had stretched the spring in the opposite direction, you see that the displacement started in the opposite direction and the velocity was in positive direction because it is now coming in this direction. Okay, you could have said that, okay, I want to make initial displacement 0, but I want to give some amount of velocity initially. So yes, you are given some amount of velocity. Basically, this is like simple harmonic oscillator is at equilibrium position, and you hammered it, and now it has started oscillating. So starting from 0 position, it has started oscillating. Okay, so all these different conditions one can check and one can show that. Okay. Now I will go for damping conditions. Okay, so let's suppose there is small amount of damping. So I make it 0.1 damping. And you see that the entire oscillation has started damping. If I take more iterations, say I go for T max equal to 50, okay, and you realize that the amplitude is falling as per the logarithmic way. Okay, so you see it is exponentially, I mean, it is logarithmically falling amplitude. Okay, and we expect that is the solution. So numerical method has this advantage that even if I don't know what is going to be the nature of the solution, as long as I translate the differential equation correctly into the difference equation, we are going to get this. Okay, where the errors can creep in, as I said, the error can creep in if I use a slightly wrong procedure. For example, I had initially, how did I realize that I have made a mistake? Let me tell you that, because it is quite possible sometimes you will also do that. Okay, so I had originally thought, okay, let me put acceleration based on the velocity and displacement. So I had put this formula equal to minus, let me give you that, minus $E$2 into x, which is d phi, okay, and minus okay, let me right now not write because I'm keeping damping term constant 0. So let me just write minus kx here. Okay, and I can use the same formula down, but here I had used the earlier acceleration. Used here d phi in place of the new acceleration, and I had done the same thing for velocity. And now let me copy this, whatever wrong formula I had entered, and see what happens. The small error goes on increasing, and it is giving me the amplitude higher and higher and higher. Okay. If some of you had carefully observed earlier when I had put t equal to 10, if you had carefully observed that it was crossing this one line, and that is where I picked up that probably I made a mistake. Okay, so uh, let us go back to what we had done.
May I interrupt, Mahesh?
Yeah, please.
This is if time permits, then I would like you to make these changes and
Sure.
Try showing one more problem, if time permits. If time
Yes,
permits.
yes.
I would like to share my screen if I am allowed.
Yeah, please. Let me stop this. You can share. Hello.
Yeah, I'm doing it. I'm
Yeah.
opening a
Okay.
PDF. You'll know what I'm doing. You
Okay.
already
Okay.
know it. It's Can you see this? This is a page from Feynman lectures. Can you see?
Yes, I can see.
Yeah. See what he is doing is just look at it. When you take position, displacement or acceleration, say displacement as velocity into time, you
Correct.
need to take the average velocity during the interval. So what he has done is the first step, he has calculated at half interval.
Yes.
Yeah, and then these are alternate. Position and acceleration are calculated at in some interval and velocity at alternate intervals.
Okay.
I'm not sure how to incorporate this in Excel. So that was one reason why I was waiting, and I didn't feel like disturbing you. But since you are going to make some changes, I thought I would show this to you. You are aware, you are anyway aware of it. But I thought I
Uh,
will point out how to
yeah. Right.
incorporate it.
Right.
And
Right.
and and okay, I'll stop sharing. The second problem I want to point out, if time permits,
Yeah.
that I would like you to do it. Is if you take I have stopped sharing, so now you can share.
Okay.
If you take simple pendulum oscillation equation, we
Okay.
take approximate sine theta equal to theta.
Fine.
So if you don't take that approximation, it will give you a time period which is not 2 pi root L by G, but slightly different.
Right. That we can do
And
there
that
itself.
yeah, that you
When
can
you are
show only
writing,
numerically.
when
That
you are
you can
writing
show
instead of
numerically.
minus kx, you can write minus sine of kx, minus k of sine k sine x.
Yes, yes. And I'm not sure whether amplitude would have a role to play on time period, if it can be seen. If you can quickly show, if time is there with.
Let us look at it, because that's an interesting problem itself. So what I'm doing is,
No,
instead
just
of
explain in detail to all the people, because I
yeah,
know
yeah,
whatever I
right,
said is very, very brief. You understood. Let everyone understand what I'm saying.
fine, fine. Let me do that. I don't have to change velocity displacement things. Okay, there it has made some circular reference. Let me just see what it has done. Uh, okay. Am I using acceleration from the earlier value? Yes. So this formula is correct. Let me just put this formula back in the two cells. Not here. Yeah. Okay. And yeah, what Professor Modi suggested is this, that forget about damping at this moment. Damping we are going to keep 0. We are writing equation f is equal to minus kx. Okay. Minus bb is obviously there. When it comes to simple pendulum oscillation, this restoring force there, okay, we are talking about there actually not restoring force, but the torque acting on the pendulum, and that torque is not proportional to theta, but it is proportional to sine theta. So can we simulate that here? So what we need to do is, in place of writing x, we will have to write sine of x, and of course x is considered in radians. So what I'm going to do is, in place of d phi, I'm going to write sine d phi. Nothing else changes. Okay, the velocity term and other things are not going to change right now at this point. Okay, and let me just put that here. Okay, so what you observe again over here is, yeah, I've taken already 50 oscillations. The amplitude or the velocity or the displacement, whatever it is, okay, it is remaining same. It is not increasing. Okay, so even if I take instead of 50, say if I take 100, okay, you see that amplitude is remaining constant. It is, but the point is time period changing? That is a question. Okay, and that one can observe by carefully there are multiple ways of doing it, but carefully observing what is the peak value here and what is the peak value here, and here it turns out peak value slightly below 2. Here it turns out, okay, let me take these peak values because the time periods are same. So for this red curve, which is velocity curve, okay, from this point to this point, the peak value turns out to be approximately around 2 pi. Okay, now if I increase the amplitude, what happens? That is the question. So I make velocity larger. Sorry, can't be too large. So effectively, this is increase in the amplitude or increase in the energy of the system. And here you clearly see that this peak is near about 7, right? Is that clear? Is that visible? The red peak here I am showing. Am I
Yes,
there
sir.
on the?
Yes, sir.
Yeah, so the red peak
Yes,
which
sir.
I am showing is more close to 7, and in the earlier case, when it was 1, you see it has shifted here, okay, which is less than 7. So yes, as amplitude goes on increasing, the period increases. We expect that because when you solve analytically the simple pendulum, what happens is you get the elliptical functions, and when amplitude becomes sufficiently large, the period is supposed to increase. So yes, we do observe that. That's fine.
Yeah, one more thing. Just look at the shape of the curves.
This curve
It's
particularly.
no more. Yeah, it's
It's
no
no
more
more
remaining
sinusoidal.
sinusoidal.
It's no more.
Yeah.
I mean, it is a periodic, but it is no more pure sinusoidal, which means the higher harmonics will come when you want to explain this particular curve. Yes. So good. I mean, thank you, Atul sir, to add this. Okay, that this is something additional feature we can study while playing with these things. Okay, let me go back to the old formula where we are talking about simple harmonic oscillation. Okay, and let me go back to the old condition. It doesn't make a difference whether I use this condition or that condition. And let me go to say 50 oscillation. Say the time of 50, so that there are multiple oscillations. Now, what we are going to observe here is if I want to plot a phase space. What is phase space diagram? In mechanics, phase space diagrams are very useful, important. So when you plot momentum versus displacement, okay, the plot you get is a phase space diagram. Now this is for simple harmonic oscillator. What is the phase space diagram? So you need to plot V versus X or X versus V. Generally it is Y-axis is V. So what I can do is I can start plotting directly the chart first, and then I'll select the data.
Sir, can I ask one question?
Yes.
Sir, right now velocity is based on previous cell, or is it using the adjacent cell of acceleration?
Velocity is using acceleration at the same point.
Oh.
Simple harmonic oscillator. Let me just write this part. And X, I want this. And Y values I want from velocity. Basically, it is velocity into mass, but it is proportional to velocity. And what you observe is the ellipse. Okay, I mean, depending on how you stretch it, it is basically an ellipse. So simple harmonic oscillator phase space diagram is going to be an ellipse. What happens if there is damping? So you get a spiral. So it starts at this point, but then it spirals down, and you can see that the energy is decreasing. Then the amplitude will go to 0. It will come down to the origin center. Okay, so you can quickly. I mean, you have not done extra calculation. You just plotted V versus X, and you get the simple harmonic oscillator phase space diagram. So this is a phase space diagram. Okay, is it fine? This part.
So can you show the formula for the simple harmonic oscillator that you use for calculating
Okay,
A?
I should I show you the from the presentation or from here?
So from here.
Okay, So here, what I'm doing is acceleration I'm calculating based on the earlier iteration velocity and displacement. Velocity I'm calculating based on the present acceleration into delta t added to the earlier velocity. Displacement is earlier displacement plus velocity, the present velocity into delta t, the current, this particular interval, the present interval.
So, can we add arrows in the direction of the phase space here?
No, it is not possible. I mean, at least I'm not aware how to add arrows in the direction in Excel charts. So, but I know that X was starting at 1, 0. So I know this is the starting point because this is my X axis, this is my velocity axis. Okay. If I had started X with -1, you can see how it changes. It started from here at this point. Okay. And it is going in this direction. So I may start x0 and velocity with some 1. So you see now it has started velocity with 1. So that way one can guess from where it is starting. Okay.
So here the second value of velocity is not depending on the first.
It is depending on the first. It is depending on the first. It is not, you see, it is C phi plus B phi into $A, $2. Now, the B phi itself is 0.
Right.
Okay.
Okay.
No, but it should not be B phi. Wait. It should be B6. Thank you for pointing out. It should be B6. Okay, and
because we changed it just
earlier
now.
It was
earlier,
changed.
yes. That's why I asked.
And that particular part did not get changed. Sorry.
Yes.
So, I mean, I just did undo, but not sufficient number of times probably. Okay. So yes, it does change. Shall we proceed to the next part? Or are there any difficulties in this?
One small comment, Mahesh.
Yes, please.
The area of ellipse in phase space is related to energy of the oscillator.
Yeah, thank you.
So the spiraling inward actually means that area of
it
that
is losing energy.
Yeah, it's decreasing, so energy is being lost. Just a small comment.
And yeah, thank you. And we can also calculate the energy terms here. See, I can, for example, calculate kinetic energy, potential energy, total energy terms. So one may calculate the kinetic energy terms. So this is going to be, say, 0.5 into, we are taking mass as 1, but suppose I want to write that $G, $2 multiplied by velocity square. And I can write the potential energy half kx square. So I can write this as 0.5 into k is $2 into x square. And then you can write total energy as E, which is sum of these two. This is useful exercise because, let me push the chart aside. This is going to be useful exercise because this will tell you whether your iterations are working correctly or not. Why I'm saying that? Because the energy of the system should not change if there is no damping. If there is damping, of course, it is going to change. So in this case, it is going to change because damping is there, it will reduce. But if I put, you see the energy was 0.5 and it has started decreasing, and then finally it has came down to 0.003. But suppose damping is not there, okay, then we expect this should remain constant, okay, but it is not. It is slightly, you see, it is slightly increasing, decreasing, and that basically indicates that this method does have small error, okay, and that's where that intermediate values and the better resolution values need to be taken. Over a long time, it doesn't affect because it is an oscillatory solution. So what happens is the positive errors and negative errors effectively cancel. But otherwise, it is going to introduce small amount of error. So if you had a monotonically changing function, okay, then probably the errors will go on getting added. So that is one observation here. Okay, so calculation of kinetic energy, potential energy, or calculation of total energy in the system becomes a useful exercise whenever you are doing simulation, because that tells you whether your simulations are working correct, whether errors are kept in, okay, because of the probably simple method that you are using. I'm using a very simple method here. Okay, so the errors could be creeping in, but oscillatory nature may probably compensate, okay, that positive and negative part of the error.
Sir, one more thing, sir. Sir, this graph, sir, what is the x-axis and y-axis of this graph?
The x-axis is a displacement, y-axis is the momentum. In this case, actually velocity, which is proportional to momentum.
Okay, sir.
It is a phase space diagram.
Okay. Okay, sir.
So, yeah.
Sir, we can plot graph between Ke and P and see at which point those get equal value, at which point K is highest and P the lowest.
Yes, all those things can be done. In fact, what you can also do is, this is a place where you can use those index match functions, and you can decide within what resolution where the energy is, or the kinetic energy is becoming peak, at what value of the index it is becoming peak, and so on. So all those features of Excel surely you can use. Okay, you can also find out okay, what was the maximum value of E. I can just write and find out the max of this, and I know that it has increased, point instead of 0.5 it is 0.512. Now what is this 0.512? If I double it, it is 1.024, which means I'm introducing an error of about 2.4%, 2.5%. So 2.5% is the maximum error that I have. Okay, and this is how, when you are doing numerical integration and differential equations numerically, okay, the different methods tell you, analytically people have worked out that what is the maximum possible error involved with that particular method. Okay, so one has to take that also into account. Fine.
Yes, sir. Thank you, sir.
So what we are looking at is how simulations can be built up, but simultaneously how one can take into account the how one can find out where could be the source of error, and how much could be the error. So we know in this particular problem energy is supposed to remain constant. So when you calculate the total energy and you realize that it is increasing, so you can find out how much is maximum. You may also find out what is the minimum value and whether it is compensated almost equally. Okay, so yeah, we expect that it should be compensated almost equally. If it is not compensating almost equally, what it would mean is the distribution is not equal on positive and negative side. This is what it would mean. But you see, here they are compensating. If I add the two, this plus this, I should get twice 0.5. And yeah, I'm getting that. Of course, there is even small error in that, but you can see effectively that error is in the fourth significant digit. Okay, so fourth decimal place, the first significant digit being 1 can be neglected. So basically fourth significant digit. Okay, so all these things one has to keep in mind, whether you are working in Excel, whether you are working in Python, or any tools that you are using for numerical simulations. Okay. Let me go back to
Mahesh, a small comment.
Please.
This is for you. I'm sure you will give them some assignment for working out.
Yes.
They can try solving a planet in the field of sun, gravitational field. So
Yeah,
they'll
sure.
have to
In fact,
calculate.
that on Monday, Nishita ma'am is going to discuss in her session.
Yeah, but in Excel,
Also,
whatever you
in
have done.
Excel, in fact, that was my next thing. What is the how
Okay.
one can handle and write equation? That is what I wanted to discuss in 2 dimension, because 1 dimension many times becomes simple. In 2 dimension, what you need to do.
Yeah. So so you
I will
calculate
give
X,
hint. I
X
may not
position and
calculate
Y
here.
position. Yeah, X
Yes.
position and Y position. And if you make a plot of those X and Y positions successively,
Yes, you
then
will get the
it will
orbit.
give you the trajectory.
Yes.
Yeah.
So
Thank you.
I'll be,
Sorry
yeah,
if I've interrupted.
that's fine. That's no problem. Yeah. So let me share the presentation and continue with that. Okay. So for the next part was you go to 2-dimensional problem. Okay. Like for example, just now Atul sir mentioned that how do I work with a trajectory of a particle, say around sun? Many mentioned that around sun. What basically it means is you are considering one body very, very heavy. Effectively, it is not moving because of the mass of the other, or because of the gravitational force of the other. Okay, but it is not necessary that you work on such kind only. It is also possible that you may take equivalent masses and both are moving around common center of mass. Let us look at how we are going to deal with how we write this equation. So first thing is you write this is a force equation. So force is equal to minus g m1 m2 upon r square r cap. Minus sign indicating that it is an attractive force. It is inverse square law, and r cap tells you that it is a unit vector in the radial direction and it is radially inward force. Okay, g m1 m2 depending on the situation, you may take it as one entire thing and accordingly work, or you may substitute. Suppose you want to work only in SI system of unit, then you may put the value of G okay as what is 6.67 10 to the minus 11. Then mass of M1 and M2, the planetary mass, like for Earth it is about 6 into 10 to the 24, Sun about 2 into 10 to the 30, and so on. You may do that. But we are more interested in how to write this. So unit vector, radial unit vector, remember, is a bit more complicated. It is cost. I want to write r cap. R cap in xy coordinate system is cos theta x cap plus sin theta j cap or y cap. Okay, so its x component is cos theta and y component is sin theta for unit vector. But we don't actually need to do that. We can rewrite this entire expression as r cube into r bar. Okay, and now it is easy to resolve this, because then I can write the x component of this is x component of this. Now out of which this entire thing g m1 m2 by r cube is can be calculated. It's a scalar quantity only. Okay, and r bar x component is nothing but x, and y component of r bar is y. So you may straight away write this. And what is r cube? We know r square is going to be x square plus y square. So r cube should be written as x square plus y square raised to 3 by 2. Okay, because r square is x square plus y square. So r is root of x square plus y square. So r cube becomes x square plus y square whole bracket raised to 3 by 2 or bracket raised to 1.5. So once you do this, then you go back. Basically, it is 2 simultaneous problems, okay, of the earlier kind. So based on F force, you will calculate the acceleration along x direction, acceleration along y direction, velocity along x direction, velocity along y direction, displacement along x direction, displacement along y direction, and you can then simulate the entire thing. So it is possible that you can do this. I'll just show writing the expression here. Let us. One part is already ready. The second part we need to write. Let me call this as AX, VX, and X. And I'll write
Excuse me,
AY,
Sir,
EY,
screen is
Your
not
screen
shared.
is not
Y.
visible.
Yeah, I have to share this window. So the same thing I used here. Now I don't talk about KB and M and so on. Okay, so it gave you 0. We'll take that into account. The initial position also we need to look at, but we need to now give the initial position, initial velocity. It is second order differential equation in 2 dimensions. So we need to give initial position, initial velocity, but position and velocity are going to be the 2-dimensional vectors, and basically therefore we'll need 2 components of initial velocity and initial positions. Okay, now let us write first what are going to be the expressions for acceleration. So that is what we calculated. Acceleration, I want to write minus g. Now let me write g somewhere here. 6.67 e minus 11. I'm right now using mass of sun. I'm right now using SI units. But if I don't use SI unit, that also is at times fine. I will calculate 24. This is yeah. The 3 basic things are clear. Acceleration. Remember what was the formula? Minus g into m. M is mass of the sun. The mass of the planet is actually not required here. So $F $2 into mass, but then I have to divide by the same mass of the planet. So that part is not required. And what was that? Minus g m1 m2 x upon x square plus y square raised to 3/2. Okay, so multiplied with x value. Okay, divide by x square plus y square raised to 1.5. Now, of course, the displacement I have put position as 0, therefore it is giving me divided by 0. But I will put the position of Earth again in SI unit. It is about 1.5 10 raised to 11. I'll put that. I have to calculate velocity. Okay, I have to write expression for A in y component of A also. So minus $E $2 minus GM $F $2 minus GM multiplied by y divided by x square plus y square. So this square plus this square raised to 1.5. So what I've done, I have calculated acceleration here and acceleration here. And what you observe here, I have put the same formula. I mean, the y component, x component. I have given x component, which initial position along x component is initial position is along say x direction, and y direction initial position is 0. Okay, so there is no because the sun is at the origin and the planet is at along x-axis. There is only acceleration along x-axis, or rather negative x-axis, and there is no acceleration along y-axis. Okay, I need to calculate velocity and displacement, and I will have to also give initial velocity. Okay, but let us physically see what that initial velocity should be. But formula is going to be independent of that. So velocity will be calculated in the same way: earlier velocity plus the present acceleration multiplied by this $A $2. Okay. Similarly, the present, I mean, this new position is also going to be calculated like that. pi component of velocity will also be calculated like that. So you see it is F5 plus E6, which is AY. So that's an advantage of writing AX, VX, X together and AY, VY, Y together. Quickly I can copy the same formula because the relations are similar. I need to put velocity because if I just keep it, if I just keep a planet at one position without any velocity, it is directly going to bang on the sun. So imagine there is a sun at the center here, okay, and Earth is here, and it is moving in an anti-clockwise direction. So if it is going to move in anti-clockwise direction, the initial velocity will be tangential, and it will be y velocity. Okay, so we know y velocity for Earth is approximately somewhere around 29 kilometer per second or so. So I want to put right now that value of say 2.94. Okay, 29 into 10 raised to 3, so 2.9 E4. This is what I'm going to keep beginning. Initial velocity along x direction is going to be 0. This is what I'm taking. Let me iterate all this up to say G1005. And time interval I need to decide because this is in seconds that we are talking about. Okay, and what has happened? Y has changed to some different position. Now let me plot x versus y, and you will see that it would not progress much. Insert, scatter this. Let me keep the same scale. If the scale is different, then okay. So I'm going to keep this as minimum value as minus say 2E11, maximum value as 2E11, and here minimum value of minus 2E11. Why I'm saying 2E11, basically it is 1.5 into 10 raised to 11 is the distance of Earth from Sun in SI units, in meters. So I'm keeping this range.
So,
Yes.
in the formula of acceleration, you have, I think, missed one factor of m2.
Yes, I have not used one factor because acceleration is going to be mass upon
Okay,
the,
so you have divided.
yeah, force upon mass, right? So I've divided by that. Okay. Now I go time. My maximum time I'm going to take somewhere around say, let me take 1E5. Now after 1E5, okay, let me just explain what is happening. 1E5 is 10 raised to 5 seconds because I'm reading everything in SI unit. 1E5 is 10 raised to 5 seconds, which is 1 day. And you see in 1 day it has slightly moved. Okay, I need to go to basically 1E7 or something like that. Okay, that will be about 4 months or so. And you will see that it has moved this much. Okay, basically 1 year is approximately 3 crore seconds. So if I go something like this, you get the complete circle. Okay, this is how the planet is moving now. Okay, and you can now play with various different kinds of things. Suppose instead of giving this velocity, okay, which gives me almost critical velocity, so that body moves in circle. If I give a very small velocity, if I give instead of 29 kilometer per second, if I give maybe just 15 kilometer per second, 1.5 E4, which is 15 kilometer per second. Now see what has happened. I have given less amount of velocity and it has gone into elliptical orbit. I can increase this velocity instead of 2.9 into 10 raised to 4. I can make it 3.5 into 10 raised to 4. And you see that it has gone beyond the scale because the orbit has become really large. And what I can do is I can increase that scale here, a minus 3 plus 3. And here also I can increase that scale, minus 3 to plus 3. Now see what has happened. I have given larger velocity. I mean, let us look at the physical significance. I have given the larger velocity. So larger velocity means now it is going to move in an elliptical orbit. But this point, the point of starting, is having velocity greater than the critical velocity, and therefore what happens is this becomes a perihelion position, the closest position, and it has got sufficiently high energy so that it can go sufficiently long distance also. And when it can go sufficiently long distance, okay, naturally it is going to take more amount of time. So this time of 3 crore seconds or 1 year is not going to be sufficient. Okay, so I may slightly increase instead of say 3.5. This is like 35 kilometer per second. I may just go say 3.2 or 32 kilometer per second, and you see that well, within 1 year it will at least complete this much of revolution. So it is still going. You see the right hand side, it is close by. The left hand side is far off. It has in fact gone beyond 2 into 10 raised to 11, okay, which is, I mean, it started at 1.5 into 10 raised to 11, so it has gone beyond 2 into 10 raised to 11, okay, and you can imagine then that this could be a perihelion position. Now, not necessarily that exactly opposite point should be perihelion position. That can be even shifted at some other location. And how do you do that? So you may add one more column here to calculate what is the R value. So I may calculate R, and I can R is going to be what? X square plus Y square. So this is going to be, or square root of that. So square root of X square plus Y square. And I can do this calculation till the end. I can find out what is the maximum value. So you see the maximum value goes somewhere around 2.03 into 10 raised to 11. This is not going to be precise. This is going to give you some idea. As we have already discussed, this method will have small amount of errors. So this is not going to be the precise up to whatever number of decibel we are saying. We need to bother about where exactly the errors are increasing. And how do you calculate the error? You can calculate the error again by putting a formula for energy. Okay, you have to calculate now potential energy plus kinetic energy. So right now I'm not writing out that, but I hope from the earlier example it got clear to you that we expect energy to be constant. So when you are using numerical simulations like this, it is not necessary that always energy will remain constant. Okay, because there can be errors involved in your step calculations. Okay, so in the next week, along with the new problem that Nishita ma'am will be discussing, okay, in the afternoon tutorials, some part we expect you also to estimate the error in each of your simulations. Okay. Anything, Professor Modi, would you like to add?
Sure. Can we find systematically the velocity at which it will escape the gravitational pull of that body?
Okay, so now see, that's a good question. That can I go on increasing? Can I systematically go on increasing the velocity and find out where it will go? But you see, what is the guarantee? So I'll give an answer also. But suppose I just go on trying and I look at the graph. What can happen is the distance will go on increasing, but what is the guarantee that it will not come back after, say, 10,000 years? I mean, we are assuming that only sun is there and only sun is going to affect its path. Okay, so best way
Yes.
of doing that calculation is you calculate the total energy in the beginning. If the total energy in the beginning itself is becoming 0 or positive, then you know it is going to escape. For a bound system, the total energy has to be negative. Gravitationally bound system, total energy must be negative. Okay.
Okay.
So that,
So if the
that
energy comes positive, then there are chances that it will escape at some point.
yes, it will escape, because if energy becomes positive, it means it is no more in elliptical orbit. It is going to be in parabolic or hyperbolic orbit. If it is very close to 0, it is parabolic orbit, but parabolic orbit is just a lower approximation on hyperbolic orbit. When energy becomes positive, it is going to be hyperbolic orbit. Yes.
And sir, here the Vy remains almost constant. Why it is so?
No,
Like it
in the
looks like.
beginning, you are only looking at in the initial steps. See, as you go down, it is decreasing. You see, here it is decreasing. It has become negative. Okay, so only in the
So it
beginning
is
you are
changing based on the. Can you see? Please see that. Tell that formula again. Vy and Vx.
see velocity. The initial. This is the initial velocity. Okay, the velocity is going to be the earlier velocity, or velocity in the at the end of or at the beginning of the interval, plus acceleration into delta t. Velocity at the end of the interval is velocity at the beginning of the interval or end of the last interval multiplied by acceleration into delta t. So here
Okay.
you see initially the acceleration is very small and therefore velocity is not changing. But as y acceleration will go on increasing, you will see there is significant change in Vy also.
Okay. Thank you.
Sir,
Yes.
can we determine the time period of the planets in this way? Is it useful?
Okay, are you talking about determining time period on this numerical simulation?
Yes.
Yes, it is possible. You will go on increasing this T max, and then you can find out when it comes back. I'm saying this because you don't know exactly where because you have given initial position, initial velocity, so you don't know exactly where the aphelion position is lying. Otherwise, even if you calculate up to time period up to aphelion position, okay, then you know that double time it will take to come back. But the best way in such kind of situation is just go on increasing the T max value and see when it touches back to original point. So that will give you the time period. Yeah, and you see dt becomes very large here, 30,000. That is also going to creep in error. But as we have been saying, dt 30,000 does not mean anything. I mean, 30,000 doesn't mean that it is large. So when you say that dt should be small, how small is small? Ultimately, it will be decided by the values involved in the problem. Okay, so here we are talking about, when I calculate dt, I am only talking about 1,000 points. I can go to 10,000 points and I can do a better simulation. So I may increase this to 10,000. Okay, and yeah, I can. What I need to do is I need to put all the formulae, copy and paste to A10005, 10,005, paste. Okay, Excel is going to quickly do that. It just does that I have not updated the graph point. The graph point also should be updated. So let me select the data, and in this series, let me just put extra 0 here. And yes, it is done. So see, I mean, the procedural way it is very simple, and Excel also is designed in such a way that it can break the problem at OS level, and it can use all the processors. Of course, many of those compilers or interpreter systems will be doing that. Okay, but Excel, makes use of that. So suppose if you give really a huge big problem where you need to do a lot of calculation, okay, and your system is not very fast, then you will show at the bottom here saying that it is using 4 processors and doing the calculation, and then at the end of the calculation it will display the result. So yes, it can do that. Graph plotting has a limitation. I think only 32,000 points can be plotted. So I've gone up to 10,000, but I may not be though 1 million data points are available, you may not be able to plot all those 1 million data points in the graph in Excel charts. Okay, so the limit, when you go to more complicated problem like this, certain limitations you may observe, but otherwise things are quite simple and fast. And once you have written some basic template, you can use that template multiple times. And I suggest that the same thing you can do also for Python. Of course, in the beginning, it is useful that you write the code again and again, because that will also give you a quick practice of writing things. But you are more interested in, now let me simulate this, let me try this problem or the other problem. Once you have written a particular code for writing particular program, what I think is now you can directly copy paste the same code and only make relevant changes. I think next week Pratik will also show you those things, how to find out an error if there is debugging part. So and when it comes to syntax and other things, Jigar will surely help you in that. Okay, fine. So this was about simulating the first order, second order differential equations of these kind. Shall we proceed? Any other questions on this?
Sir?
Yes.
I am computing a problem here. It is showing that the acceleration formula is not accepting. I think I made some mistake. Can you show us the
acceleration formula is not?
It is not taking. So it is showing me some error.
Is it showing cyclic
bar.
reference error or something like that?
No, it is showing inconsistent formula, I think.
So have you written the brackets and everything correctly?
Yes, sir.
Well, this is the formula. Okay, this is the formula. I'm writing a minus G into
Sir, for X it is correct. For
M.
Y it is showing problem.
Okay, but I'm using the same formula for Y. I just copied
I have entered the same, but
Actually,
there is issue.
For AY also, I am also getting issues like my value is not changing. It is like coming constant.
Yes, it is
like
range.
That
It is saying almost same.
What is your DT? How much is DT?
DT is same as it is.
Tell me DT is how much? Numerically, how much it is?
DT is 30,000.
30,000. D max is
3 into 10 raised to 7.
Yes. Same.
Okay, so you are taken 1,000 points. Okay, and you are
Yes.
taken same Vy Y.
Yes.
Are you sure? Same Vy and Y.
Vy it is 2.90 E plus 4.
Vy is 2.9 E plus 4. Okay.
Yes.
And X value?
X is 1.50 E
1.5
plus
10 raised to 11.
11.
Then it should not.
The main part is, sir, AY is not changing. I don't know why.
No, but have you gone down to the bottommost part? Have you checked that?
Yes, sir.
Go to the last cell and does it remain same?
Sir, this inconsistent error occurs when the formula entered in that cell is not, such kind of formula is not entered
In
around
adjacent
that
cell? Okay,
Yeah,
okay.
yeah, yeah.
Is it due to
That
that?
is why
So
it
if
is
I
showing. Yeah.
okay, so
Because
if I
in
insert
first
a
screen
cell,
also it is
then
showing
it
the
must
error
go.
in E column
Yeah,
from
yeah,
E.
it's gone, it's gone. Yes,
Yeah.
yes,
So
yes.
that
Thank you
that
so
is
much.
not
Thank you so much.
No,
any problem.
okay. Thank you for so. They have understood, but I did not still understand what was
Sir,
it. Yeah.
it was saying that if the adjacent cell has that formula for circular like circular type, means it is using previous value of x and
Okay.
current
Okay.
value of v, so it is not taking that formula for acceleration. So now I inserted the cell and now it is okay.
Okay. Which means somewhere it was having a problem. I mean, it was using a reference point. That reference point itself had a problem.
Yes.
Sir,
Something
can you
like that.
please show the Vy and Y formulas or
Okay, Vy formula is the earlier. Let me click in the formula bar so you know which cells are being used. Okay, so I'm clicking in the formula bar. You see, I'm using basically 3 cells. The earlier Vy value, which is in the blue, the present Ay value, which is written in the green, and delta T value, which is here. Just 3 things.
okay, and Y value is also constant or it is changing?
Y
How it
value is
is
also
changing?
going to change. Y value is formula is again similar. The earlier Y value, the present V value, and the delta T.
Okay. Okay.
Okay. You see that initially, of course, Y values will slowly change. Okay, because you started at x equal to 0. I started at this point. Okay, so Y value is changing, but I mean, after sufficiently long time, it will surely change. If you remember, we started with very small Tmax earlier, and then we saw that, okay, I mean, I had taken Tmax something like 1000, and 1000 means I'm only talking about 1000 seconds. Even when I went for 1 lakh, 1 lakh was very small value because it is just 1 day. In 1 day, how much Earth will move around the sun? Okay, so
Yes.
let us quickly recap what all things we have done. We talked about simple harmonic oscillator problem where you are given the expression for acceleration, you are calculating expression, I mean you are writing expression for velocity, and you are writing expression for displacement. So you are dividing the entire time into different intervals. Okay, at t equal to 0 you are writing what is the initial position, initial velocity. Okay, that point you are not calculating acceleration. In the next iteration you are calculating acceleration based on the earlier intervals x and v values. Then you are calculating velocity based on the present acceleration and the earlier velocity, because it is just added into that. Similarly, the displacement is added into the present velocity multiplied by dt in the earlier value of displacement, and we are generating this entire series. For 2-dimensional problems, we need to bother about the vector, and therefore you will have this. You can also have 3-dimensional problem, but central body problem is always 2-dimensional. Okay, because the force is acting towards the center, and if it has got some initial velocity, then you know that initial velocity direction and the force direction, which is towards the center, towards single point, these two vectors basically define a plane. Okay, and the entire motion is going to be in that plane. So any central body problem can be considered to be just a 2-dimensional problem. So keeping that in mind, one does this. But if you have multiple bodies playing a role, then in general you can write ax vx x, ay vy y, and az vz z, and you can simulate everything in 3 dimension. Okay, only thing is, while plotting, you will not be able to plot all those 3-dimensional things. You will be able to plot only a 2-dimensional structure. So you may either plot xy trajectory or yz trajectory, or you want to see how velocities are behaving. So you may be able to plot only any 2 parameters at a time. Okay, so this is what we how we can simulate. More important things, there are going to be small amount of errors. We have to bother about whether the errors are increasing or oscillating, or I mean ultimately compensating to become 0. And how do you do that? One important tool is calculate the energy of the system and see whether the total energy of the system is changing. If it is monotonically changing, then yes, the simulation is not going to be very good, because it will go on adding up the error. If it is not blowing up, if it is not monotonically increasing, then you find out what is the maximum value, and you may find out what is the relative error, or what is the maximum possible error that you are getting. So energy calculation is one important tool. In this kind of problem, gravitational problem, you can calculate the velocity, you can calculate the value of r. You may also calculate the value of theta, and you can see what is r theta relationship. And you may also try to fit from r theta relationship, whether you can fit that in the, that data of r and theta that you're going to generate in the conic sections formulae, and whether you can find out eccentricity. So even that can be done. We can discuss that in one of the tutorials. Okay, so this is about simply using differential equation, or these kind of differential equations. Okay, let me go to some additional things that one can do. So let me share the presentation. Okay, is this visible now?
Yes, sir.
Yes.
Fine. Other useful problems that one can handle, and some of these expect during assignments. A few of them we will see whether we get time to discuss during next week's tutorials. Okay, you can synthesize the different waves, different Fourier components, okay, using Excel. And I will, this will be part of your next assignment, okay, where I'll give you the terms. Fourier transform or Fourier analysis is a different game. There, what you do is you are given a wave shape, and you need to work on that data and get the frequency component. But this is relatively simple. You are given what are the different frequency components with their phase relations and amplitudes. You need to just add the way you added wave packet. Okay, way you added waves to get wave packet. Okay, so we can generate Fourier synthesis, and you can see that how different wave shapes can be done. Okay, this is the simple part. Formation of wave group that we have already seen. Like gravitational field, you can also write a problem for electrostatic, magnetostatic fields. Okay, and you can do some simulations for that. Of course, here what we need to bother is when it comes to electromagnetic field, if the charges are moving inside the electric field, okay, due to their acceleration, they are also going to radiate energy. Okay, and so in reality, it is possible that in a particular electrostatic field, you may show that electron is oscillating, okay, indefinitely, like simple harmonic oscillator. But in reality, it is going to radiate energy. And of course, if you want to introduce how that energy which is radiated also one has to take into account, yes, that is also possible. But then additional equations one will have to write and accordingly simulate. Electrostatic potentials one can calculate. So you may decide that at one coordinate, XYZ coordinate, one charge is there, another XYZ coordinate, another charge is there. Then at any given point, you can calculate electrostatic potential, and one can also plot then those electrostatic potentials at different locations. In fact, you can use Excel entire spreadsheet as the graph paper, where every point, every cell can be attributed with some x coordinate, y coordinate. Okay, and you can calculate the potential, and you can write those values there in that. Okay, and you will get a spreadsheet where every point, every cell, you will have x coordinate, y coordinate, and you will also know what is the potential. This entire thing can be plotted as a surface plot, and one can see how potentials are changing. Okay, we'll see one or two examples of that. You can do projectile motion in two-dimensional problem. Again, you can not two-dimensional, two-dimensional problem. So x direction and y direction velocity, and gravitational field is a constant along y direction. But you can add damping, and you can see that how projectile motion is there. Okay, I think there is some question. Can we use Excel to integrate some functions which are harder to do analytically? Yes, we'll do that on Wednesday's tutorial. Okay, Wednesday's tutorial will handle these things, these kind of functions. Yes.
Sir, error function is one of them.
Yeah, error function, basically area under the Gaussian, we have already done, right? So see the problem, I mean, one of the assignment which I gave yesterday, we did that. Say definite integral, you want you have Planck curve, and one of the problem was find in the Planck curve of say 2800 Kelvin temperature, find out how much of energy is, how much percentage of energy is falling within visible range. Okay, and similarly you had done calculation, what is the area under the curve for visible range in case of 5800 Kelvin. And then you had taken a larger range also. And see problem number 2 of that last third assignment, what you had done, you had plotted that Planck curve. You took a very large range of frequencies. You calculated area under the curve, basically integration under that, and you divided by t raised to 4. You calculated it for two different temperatures, 2800 Kelvin, 5800 Kelvin. Okay, and area under the curve divided by t raised to 4 was constant for both. Okay, so what does that tell you? That the amount of energy given out is proportional to 4 power of temperature, because that value is constant. And when you multiply that with c by 4, you get the Stefan's constant. So many of you have done that problem. Okay, so I mean, even those integrals, okay, they are otherwise difficult to calculate for a particular range, but you are calculating easily here in Excel. So integration is calculating area under the curve. Which method you want to use is up to us, and whether you want to use trapezoidal rule because it is simple, or Simpson's rule. But Simpson's rule many times is simple. What I was talking about, and thanks for reminding that, but what I was talking about, the other kind of differential equations. So Wednesday we'll talk about those other kind of differential equations which could be harder to do analytically. So we will discuss some of those cases on Wednesday's afternoon session. Okay.
Sir,
yeah,
I have a question regarding motion in physics. Sir, is the relation between harmonic oscillator and Taylor series?
will you repeat the question?
Is there any relation between harmonic oscillator and Taylor series?
Yeah, there is a good relation, what I would say. See, if you take any potential function, what does Taylor series say? You know, Taylor series says that you can write a function. Let me see. Okay, let me switch off the video, and let me see. I can write here. Let me just add the board here. Can you see this?
Yes.
Board?
Yes.
Yeah. Okay, so if I write any function, say v of x, I can, in Taylor series, I can write this as v calculated at x0 plus v dash v dash into x minus x0 plus v double dash x minus x0 square upon 2 factorial. And all this v dash is calculated at x0. V double dash, that is second derivative, is calculated at x0. And then third derivative, again, this is calculated at x0 and so on, right? This is what we do. Now, suppose a function has, a potential function has minima at x0. What will happen? This Taylor series expansion becomes v at x0. This is going to be a constant because this is evaluated at x0. So it's constant number. That first derivative at minimum of a function is 0. The derivative at minimum is 0. Then you will write all further functions. So this v double dash at x0 is going to be again some constant. And remember, if it is a minimum function, the second derivative is positive number. So there is going to be some positive number, which I'm going to call k. Okay. And x minus x0 is the extra displacement. So that extra displacement I can write, say, as maybe x bar, okay, square upon 2 factorial, and all higher terms I can write. But now if I take that extra displacement as a small value, all higher terms can be neglected, and then what I get is a parabolic potential. So basically what I get is v of x is equal to v of at x0, a constant, plus half kx square. Okay, 1 by 2 factorial is half. If I write the force is minus gradient of potential. So if I take derivative of this with respect to x, what am I going to get? Minus kx. But this is simple harmonic oscillator. So is the idea clear?
Yes, sir.
Yeah. So yes, I mean, and that is where, I mean, I think one of the days I was talking about, I said, whenever there's a minimum potential, around that minimum potential, you can always approximate that as a parabola. Okay, so it is basically this Taylor series expansion approximation, that you are considering higher terms negligible, and it is a shifted parabola because I mean, there are shift in y direction and shift in x direction because it is x minus x0 square that you are doing. Okay, but basically it is going to be a parabola, and parabolic potential is nothing but simple harmonic potential. Okay, so now what I will do is the last thing that I was showing here in this particular simulation, projectile with air damping. Let us do that. Okay, that is also an interesting problem with the good physical significance. Okay, so let me stop presenting this and let me come back to the Excel sheet. Just is the sheet visible?
Yes, sir.
Yeah. So let us go to this projectile thing. Okay, let me delete this so that I don't have to type T again. I will need XY. So, okay, I will need most of these things. What is our equation when we are talking about the projectile motion? So projectile motion is two-dimensional, x and y. The acceleration is always along negative y direction. So that is fixed. So I can write Ay as, now let me just take the SI unit values itself again. So acceleration along y direction is negative minus 9.8. Okay, and I'm going to now decide this acceleration, horizontal acceleration. Right now I'm going to keep 0. Okay, horizontal acceleration right now I'm keeping 0. Initial velocity I need to decide, initial position I need to decide. So let me do that. And I'm going to write this till end. I will explain what I'm doing. 1005. I'm pasting it. Okay. Vy value also I need to decide what is the initial value. Okay. And of course, I mean, I was supposed to keep all this, but let me rewrite that. R I am not bothered right now. Okay. So I'm going to throw it up. So for a projectile, what are the values? You give velocity, the total velocity, and you give angle theta. Okay. Now at this angle, I'm going to give in degrees. So let me take 20-degree angle. Fine. So I'm writing angle in 20 degrees. Okay. And velocity, I'm giving something like it is going. Remember, it is going to be in SI unit. So I have to give some realistic velocity. I can't give in kilometer per second or things like that. So let me keep it, say, 50 meter per second. Okay, sufficiently high velocity. I can make it 500 meter per second also. That is also good enough. Okay. Now let me quickly calculate all these things. So again, time is very large, and I don't. I have to now here think about how much time is going to be sufficient, and we'll employ some different scheme. Let me first write the initial values of velocity. So what is my x velocity? X velocity is this velocity, the initial velocity I'm giving, $e $2 into cos theta. And because I'm giving angles in degrees, I must convert that first into radians. And I write cos theta. Okay. So this is the initial velocity that I'm giving. Fine. Initial x velocity. What is initial y velocity? It is going to be $e $2 multiplied by sine radians and this f. So $f $2. Right. This is initial velocity. I could have written F2 also, because anyway I'm not going to drag this formula down. Okay, but I've just written it. Now let me write velocity. Velocity is new velocity is going to be the old velocity multiplied by present acceleration old velocity plus present velocity multiplied by $a $2. I've done this. I have to copy the same formula here. The initial y position is 0. Initial x position is also 0. And here also I have to write formula. Yes, I have written C5 plus B6 into $a $2. And this is going to be 0. So accelerations, horizontal accelerations, all are going to be 0 initially. Later I will introduce damping also. So that time it is not going to be 0. Okay, whether I am taking 1000 or 10,000. Okay, let me take 1000 points maybe here. So let me go to 205. Anything beyond this, let me delete. Fine.
Sir, can you show the formula for Vy?
Yeah, let me do that. So Vx formula is earlier velocity plus acceleration into delta t. Similarly, y velocity is earlier velocity, that is f5 plus acceleration into delta t. And I am writing same formula for displacement. It is earlier displacement multiplied by velocity into delta t. I am going to write the same formula, this same formula here also for it is earlier displacement into plus velocity into delta t. Okay. Now what I'm going to do, yes.
Yes. I think your V0 is 20, so T max will be not more than what 40 seconds.
Yeah, I have not calculated that. That is what I'm going to. I mean, right now I have not guessed how much it is. Okay, but thank you. So what we'll get is we'll get. We'll get x going more and more negative because it will keep falling. I'm not encountering a condition that there is a ground now. Okay, I've just thrown a projectile, and probably I've thrown it from a cliff. Okay, so let me copy paste all this formula up to the last cell, P1005. And let me plot x versus y. You see the y has gone to negative and it has gone to almost center of the earth. Yeah, so yes, that's correct. That T max is unnecessarily very large. In 1000 seconds, well, 1000 seconds, is how much? It is about 20 minutes. The body can't keep falling for 20 minutes. I should have guessed that. Thank you, Atul sir. But that, I mean, those insights we need to always keep in mind. So here I'm getting projectile motion. It is as if nothing has gone up. Let me take this T max, say, as 40, and we'll write a condition. So let me take this T max as 35, and you see a nice parabolic trajectory. It is still gone below the ground that you can see at that small edge, but say it will take something like 35 seconds. Okay, or if I take 30 seconds, then it has not yet reached the ground. Okay, we can of course put a condition that Vy should not become negative. If it is Vy is going to become negative, we will have to we can determine where it is becoming negative. We can use that VLOOKUP formula. Let me just do that for here. Okay, I'm going to use T max as 50, and I want to find out where exactly at what time it is becoming negative. Okay, so I am getting some value over here, but if I had not plotted, I will use this formula VLOOKUP. And the syntax is I want to look up the value. So lookup value is I want to find out when it is going to become 0. Fine. And which array I want to see. So I want to see this array. Sorry. Lookup value is 0. I want to look at this array. And third thing is I want to find out the column index. Okay, I want to give the it says A5. Syntax error. We look up value 0 table of
It can exactly become 0. You just look for the first time when it becomes negative or less than or equal to 0.
okay. What I can do is I can find out the minimum value, absolute of minimum, because minimum could be negative. So I can find out absolute of minimum. So why is it giving me this? Okay, the minimum or absolute, sorry. Okay, see, those things also make difference. I have to first find out the absolute values of all this and then minimum of that. Okay, so it gives me 17. Now where is it 17? So here I may look for that match this, sorry, index this array, then row number. Why am I doing this? Sorry. Lookup value, this array, and okay, it is not going to exactly work sure, but it is not going to exactly work. I mean, this is match because it is not sorted. It decreases and then again it increases. So let me just find out where it is. 17.02. But the 17.02 here is here itself. So there is a mistake. Okay. Right now, I'm not immediately bothered about that. It goes somewhere over here, and I will. I mean, I'm calculating at about 50 seconds what is happening. Okay, we'll work out this. What I mean, how to determine where exactly y becomes positive to negative. There are other crude ways, like you can go on checking if the earlier value of y is smaller than the next value of y or larger than the next value of y. Okay, then you can raise the flag. Then you can say that you can put if condition and you can say 1, and then you can determine where the 1 is. So those things can be done, but I wanted to do some elegant way. Let me do more important thing, which is
can you not scroll down and see positive and negative where it changes?
yes, it's possible, but for 1000 points I was a bit lazy to do that. And in this case, it is not becoming, but if I make it 50, yes, it will become. So see here, it is becoming at this point. Okay, somewhere between 34.85 seconds to 34.9 seconds, it is becoming 0. Yeah. Okay, so let me write then this as 35 seconds. So it is almost reaching 0, slightly going below. I am more interested now in the damping factor. Okay, so I'm introducing some damping factor. I'm going to call it B. And how do I put that damping factor? So you see the acceleration is not just a constant quantity, it is going to be also dependent on the velocity. And that is where this damping factor is going to come. I'll say the first value anyway, I don't need to write acceleration. In the second value, I'm going to say this acceleration is minus 9.8 minus $h $2, that is this value, whatever value I'm going to put over here, multiplied by with the Vy value, okay, in the earlier interval. Fine. Similarly, in ax value, the acceleration is not going to be 0 now. It is going to be minus $h $2 multiplied by Vx value, okay, in the earlier interval. And let me paste this formula everywhere for acceleration. And it is only acceleration is going to vary like this. Velocity is going to not change like this. And you see here, and this is something very interesting. Right now that it is still a parabola because damping is 0. But I increase the damping. You see what has happened. Now this is 0.1. First of all, the upper, the height also has changed. Let me keep it this. So it has gone up to say 1500 meters. Okay. But moment I make this 0.1, or let me make it 0.01. Instead of 1500, now it is not even reaching 1400. Okay. Let me make it 0.05. It is not even reaching 1000 meters. Moreover, it is no more a symmetric thing. What is the physical significance of this? The physical significance one of the significance you realize is it is not just, vertically, of course, there are two factors which are playing role, but you see horizontally the velocity is decreasing. So what is happening is, because it is moving, see earlier if damping was not there, the velocity along horizontal direction would not have decreased. Okay, now what is happening is velocity is decreasing along horizontal direction. So after reaching peak, it is going to fall in a short time because velocity has reduced in horizontal direction. So the time required to go up and time required to come down is not same. Also, you can observe that range is not going to be maximum at 45 degrees. Okay, let me keep B0 here. And right now, okay, let me change the number format so it is easily readable thing here. I see a number with 2 decimal places. So it is easily readable at least. Now let me take the range as 45 degrees. The time required is not sufficient. Okay, let me take time as 70 here. It has not yet reached 75. It has gone further down. Okay, at 72, some trial and error I was doing. So at 72 seconds, it has reached here. And how much is the range? The range you observe here, this of course you can calculate. You can calculate what is V max, right? Equal to max of Vx, sorry, not Vx, x entire range. And this also, let me change the format so it is better readable for low values. So you see 25 kilometer. Okay, the projectile is moving. The initial velocity was given as 500 meter per second. 25 kilometers is moving. Now, if I introduce B 0.05, so it is sufficiently skewed, and I don't. It doesn't need 72 seconds. Let's suppose it is 765 seconds. Okay, or 60. Now I change. Okay, now what is the value here? You see the 6,600 meter. Okay, so 6 kilometer. From 25, it came down to 6 kilometer with this particular damping factor. Now I'm interested in increasing the range. So instead of 45 degree, if I take say 43 degree, you see this value has increased. It was earlier how much? For 45 degree, it was 6602. Now at 43 degree, 6828. I make it further down, 41 degrees, it has gone to 7 kilometer. Make it further down, say 40, it further goes to 7.1 kilometer. I make it 38, it has further gone up. I make it 35. Okay, I mean, this is not a range. The range is only when y is equal to 0. Okay, but you can see that it is still becoming larger. Okay, and if I take say 25. Okay, this is somewhere around 7,500. Of course, this is not the range, but you can look at where it is cutting the x-axis. And if I take it 20, now see it has again come down. So what is happening here, you see here, if this is visible to you, where it is cutting. So it is cutting around 7,000 again. So if I increase this angle to say 25, yes, it is cutting somewhere around 7,300 or so. If I make it further large, say 30, Again, it is approximately at the same distance. So if I make it 28, okay, it is almost same. It is not changing much. So small variation, of course, one can check there. But if I go to something like 35 or 40, it comes down again. If I take it 45, it is below 7,000. Okay, so the point here is when damping increases, the maximum range is not at 45 degree, it is at smaller angle. So some of these things which you may not be able to do analytically very easily, quickly you can calculate using this numerical way. And then of course you can play around with this, and you can have no additional logic as we are talking about. I want to find out where it becomes zero. So y is going on decreasing, and I want to find out where again it is increasing. So if it is increasing, which means the present value should be greater than the earlier value. So I can write a condition equal to if this value is greater than earlier value, okay, then I'll write 1, otherwise I'll write 0.
Numerical value, Mahesh.
uh, Absolute value, right? Okay, so here it is increasing. No, I don't want to find out that. I want to find out when it becomes negative. So I can straight away write here. Okay, I can also find out what is the height by that, but I can just find out if this is greater than 0, write 0, else write 1, and you can apply it to H1005. And here you may use that match 0, no, match 1 into this array and exact match. So it gives me at 941, this is going to happen. So you can check then. We go to at I mean 941th value. I'm starting with no 5. So at 946, I'm getting 1. So here you can do that. I mean, you can raise a flag saying that whenever it becomes positive or whenever it becomes negative, make it 1, and then you can find out, match that. Remember, match function works best only when that particular array is sorted out. Okay, so if it is becoming positive, negative, then it will not work. But here it is monotonically changing, and therefore I am interested in where it becomes negative. So I can find out that. Okay, so the two things that I wanted to focus on this is there are problems which we had at undergraduate level sweep below the carpet, saying that if there is damping, okay, terminal velocity people find out, but at what angle the range will become maximum. Those kind of problems we didn't bother about. Okay, you can handle those kind of problems numerically, and you will have to play around with the numbers, and you can find out, well, what happens to this range. So these kind of things can be handled, which analytically were relatively more difficult. Okay, so with that, okay, my today's discussion is over, and more assignments with new tutorials will meet next week. But if you have any difficulty at this point, you can ask.
Are you giving the schedule for tomorrow?
I have already put that on the group. schedule for second week. I will put that again. Yeah.
Sir, if the assignment is submitted after due date, as you said, would
Yes.
there be any negative markings?
No, I mean, many of you were struggling, I know, with this. So, not negative marking as such. Okay, we want you to submit maximum assignment, and the reason we put this Sunday is so that you be in time and you complete that, so that you are ready for more complicated things in the next week. Okay, that's why this Sunday's deadline was given. But you may put assignment tomorrow, day after tomorrow also, but try to complete them as
Yes,
much
sir,
as you
actually.
can.
Okay, sir. Thank you.
Yeah, welcome.
Thank you, sir.